Okay, so thank you very much for being here. My name is Vittorio Erba, and today I would like to talk about optimal denoising of rotational invariant rectangular matrices. So this is joint work with Emanuele Troiani, Florent Jacala, and Lenka Zdeborova in EPFL, and Antoine Maillard in ETH Zurich. So let me start by the problem definition. So our problem is we are given a signal matrix, this is in green, S star. This is a matrix M times P, and this is extracted by some distribution, P signal. So this will be our prior distribution. And we perform a noisy observation over this matrix to obtain an observation Y, here in orange. The noise distribution is the distribution that generates our observation. This P noise of Y given a star. So it takes a star, puts some noise, and spits out Y. So our objective is, given the knowledge of the observation, so a particular instance of the observation, and on the generative process, so the distribution of the noise and of the signal, to retrieve our best guess of the ground truth signal S star. And in particular, the questions that we may want to ask are what is the expected error of this procedure, and what algorithms can achieve this performance. Notice that here I'm speaking about optimality because the statistician knows everything possible about the problem, so the performance he will obtain are in this sense optimal. And in particular, for the rest of the talk, we will consider the case of Gaussian IID noise, so a particular choice for the noise distribution P noise. And this is simply given by our observation being the signal, S star, plus some IID Gaussian matrix Z with mean zero and variance delta. So delta will be our noise strength. Okay, so why should you care about this problem? So my particular motivation to study this problem comes from another problem, which is matrix factorization. In matrix factorization, the setup is really, really similar. We have an observation of something here in green plus noise. And our something here, it's not anymore a single matrix S star, but it's a product of two matrices, F and X. And the inner dimension of this matrix product will be denoted by R. So while in denoising, we may want to find information about the product of the matrices F and X. In matrix factorization, we would like to access information about the single factors F and X. And these models, many problems in modern data science, like dictionary learning, sparse PCA, and more. It's a really interesting problem with a lot of applications. So this problem has been studied a lot in the intensive rank regime, in which the internal dimension R is much smaller than the external dimensions M and P. And in this case, the base optimal and mismatched analysis was performed. There were some observations about universality of the choice of the output channel, for example, phase transitions for in particular priors, you name it. There have been really a lot of work. Sadly, all this work translates really poorly in the extensive rank regime, in which the internal dimension of our pair of matrices F and X scales or is of the same order of magnitude as the external dimensions M and P. So in the literature, we can find some insights on a possible theory to tackle the base optimal case of this problem, but there has been no real progress yet. In some sense, extensive rank breaks our usual analytical approaches, like, for example, AMP or replicas, to be able to characterize this problem in the average setting. So this is my motivation for studying denoising, because I see denoising as an easier problem than matrix factorization, with a particular choice of factorized prior, And we may hope to understand a bit about the role of this extensive rank and maybe devise some analytical tools to be able to then tackle the extensive rank matrix factorization. Okay, now that I've given you a bit of motivation, let me focus on some details of our setting. So we will be working in the high dimensional limit. So the dimension of the matrix M and P will scale to infinity with a fixed ratio. P over M equals to R1. So R1 will be our aspect ratio of the matrix. R1 equal 1 will be a square matrix, and R1 different from 1 will be a rectangular matrix. And while our result hold for a large class of priors, we will focus mainly, for example, when showing numerics on the factorized prior. And in this case, motivated by matrix factorization, I will focus on the extensive rank. So the internal dimension of the product F and X will scale to infinity with a fixed ratio with respect to one of the external dimensions, which we'll call R2. So R2 will be our, say, rank ratio. Rank is not exactly the correct word because R2 can be bigger than 1. So we can have internal dimension larger than the external dimension, but it gives the idea. Okay, the second requirements that we do to our specific setting is rotational invariance of the prior. So rotational invariance means that the probability assigned by our prior P signal to a certain matrix S must depend only on its singular vectors. In other words, if we take any pair of matrices U and V, which are rotation matrices, and we perform the matrix product U times S times V, the probability of observing this product of matrix must be the same as observing the original matrix. So in some sense, rotational invariance will allow us to, it's a powerful symmetry that will allow us to simplify a bit our problem. Indeed, it will allow us to go from an M times P dimensional problems, a full metric size problem, to a spectral problem in the singular values of the matrix of the matrices that we will be dealing with, which is the minimum between M and P. So we are going from, let's say, N squared to N dimensional problem. Nonetheless, this class of priors is non-trivial. Rotational invariant priors are, in most cases, correlated, meaning that the entries of the matrices are correlated, and meaning that the denoising problem will be non-trivial. If we had uncorrelated prior, the denoising problem would be really simple. You just denoise every single coordinate of your observation matrix independently, as the noise was IID. And finally, I have to tell you what is my measure of quality, meaning how do I know that I recovered properly, or how do I measure how well have I recovered my signal? In our case, it will be the average mean square error, also called MSE in short, which is the L2 distance squared between the original signal S star and our guess S at of Y of the signal. And we will look at this error in the average setting. So we will average over possible choices of the ground truth and over possible realization of the observation given the ground truth. So let me give a first round of results that we are able to obtain in this setting. So the first thing we are able to obtain is the base optimal estimator. So an algorithmic procedure that gets the observation Y as an input and gives us an estimate of the ground truth in the optimal way. How does this work? So as our problem is rotational invariant, the first step that our algorithm does is quite intuitive. It will perform a singular value decomposition of our observation matrix. So we will obtain a matrix U of the left singular vectors, a matrix V of right singular vectors, and a diagonal matrix of singular values. Of course, due to rotational invariance, we cannot hope to obtain any information on the singular vectors of our signal better than taking directly those of the observation. So it makes sense that in our procedure, the singular vectors stay untouched, and we only denoise the singular values. So this is kind of a qualitative hand-wavy idea, but this is what we see also in the computation. So this function psi here, I will call a spectral denoiser, and it is a nonlinear function which gets applied on each singular value separately. After having denoised the singular vectors, we perform the matrix product back and obtain our estimate of the
recording stopped.
Oh. Is everything all right? I heard some recording stop.
Not working. Yeah. Please continue.
Okay.
Recording in progress.
Okay, thank you. Okay, so this is our algorithmic procedure. Now I have to tell you what is our nonlinear denoiser. So the function psi is a function of the singular value lambda, which is parameterized by the noise to signal ratio, delta, the rectangularity ratio, the aspect ratio of our matrix R1, and by, let me say, the only non-trivial dependence is on this quantity sigma hat of y. Sigma hat of y is the asymptotic singular value density of the observation. So for those of you that may be not extremely familiar with random matrix theory, let me give you a quick reminder of what asymptotic density is. So we define the asymptotic singular value density of a matrix Y by taking the large dimensional limit in the number of singular values of the matrix Y of the empirical distribution, this 1 over m sum over I of delta functions centered at the singular values. So this is the empirical distribution. And we, as I was saying, take the high dimensional limit of this empirical distribution. You can think about it as plotting the histogram of singular values of the matrix Y, increasing the dimension and looking only at the limit shape of this histogram. And the, let's say, non-trivial fact about these singular value densities is that while you may think that these are random quantities, as Y is a random matrix, and so its ith singular value will be a random variable, actually this limit shape exists and it's deterministic. So it depends only on the distribution of Y and depends, while it doesn't depend on the specific realization of Y strictly in the high-dimensional limit. Of course, there will be some finite size effect. So to go quickly back, the density that appears here in our formula is this high-dimensional limit, which is deterministic of the singular value density of Y. The second result we are able to obtain about our denoising problem is given by the performance of the base optimal estimator. So we not only obtain the optimal algorithm, but we obtain a formula that will predict the average error that this algorithm will achieve on a random signal from the prior and on a random instance of the noise or of the observation. And the formula, again, maybe it's not as simple as the first one, but it's still a function of the noise to signal ratio delta, the aspect ratio R1, and some integrals, some expectation over this asymptotic singular value density of the observation Y. Let me remark two things. The first one is that we have no dependence on the singular value density of the prior matrix of the observation matrix sigma hat of S. And this is really remarkable because you may think that there may be some settings in which one can estimate maybe from the observation itself the singular value density of the observation sigma hat of Y. and thus be able to apply the denoiser without any knowledge or with only partial knowledge on the prior distribution, so without knowing explicitly the singular value density. And moreover, these are two quite simple closed-form solutions, which is a non-trivial feature in this kind of problems. So now that I've shown you some results, let me show you some plots. So how does this performance look like? So in this slide, I will show you plots that present the mean square error of recovery, so of denoising, as I defined it a couple of slides ago, as a function of the noise to signal ratio. So delta here, when it's small, means that the noise is really low, and when it's large, means that the noise is really large. So in this case, we fix the internal dimension. So we are looking at factorized prior. So we fix the internal dimension so that it has a ratio of 0.2 with respect to the external dimension m. And we let the aspect ratio R1 of the matrix vary from 1 in blue. So blue is a square matrix, to red, which is a rectangular matrix with aspect ratio 20. And you see that the more rectangular the matrix, the better is the reconstruction error. So smaller error means better reconstruction, of course. Here, our baseline is plotted in black and is given by scalar denoising. So scalar denoising is the denoising algorithm that you would obtain if you assume that your prior was IID. In this case, you can denoise each component separately, and the denoiser is just a rescaling, an overall rescaling of your observation matrix, as detailed here on the right. So we see that using our spectral denoiser, our base optimal denoiser, is quantitatively better than performing just simple scalar denoising. Another set of simulations that we performed was at fixed aspect ratio. So we fixed our matrix to be a square matrix, R1 equal to 1, and we let the internal dimension of the factorized prior vary from very small rank, in blue here, to much larger, to an internal dimension larger than the external dimensions M and P. And here you see that R2 equal 2 means that the internal dimension is twice the external dimension. It's hidden here below the black line of scalar denoising. So in this case, we see that having a bottleneck in our product of matrix F and X provides a great improvement in the reconstruction error, while having an over-parameterized product F times X as performance which is really similar to the scalar denoiser. So our spectral denoiser degenerate on the performance of scalar denoising when the rank of our product of matrix is not constrained, while it's much better than scalar denoising when the rank is constrained. And here, in both plots, the continuous lines are our formula for the mean square error, while the dots are the numerical experiments that we did by applying our base optimal denoiser. Let me just stress that to obtain these plots, one needs to obtain analytically the singular value density of the observation matrix. One can use some tools from random matrix theory to compute it, in particular rectangular free convolutions and products. But this is very numerically unstable. So in our paper, we found a smart way that relates to analysis of random feature models to compute this spectral density. And you can have a look at the paper if you want to check out some details. Okay, so I've presented you a bit of results and shown you some plots. Now let me get a bit into a sketch of the derivation, so you get the flavor of what kind of math we are dealing with. So we are trying to solve a base optimal estimation problem. So our central object of study will be the posterior distribution P of S given Y. So the probability that candidate signal S was used to generate the observed matrix Y. And by Bayes' theorem, this is just given by the product of noise and signal distributions normalized by some normalization factor. And this normalization factor is often exponentially large in the dimension of the matrix Y. So it makes sense to define so-called free entropy, which is the intensive limit. Not limit. I haven't taken the limit yet, but in the intensive part of this normalization factor Z, so one takes the logs and normalizes. And it turns out that the free entropy is really the object that we should be looking at, because the optimal estimator can be simply related by a derivative of this free entropy with respect to the observation Y. And this is a very easy computation, 2 lines of algebra that leverages the fact that the noise is Gaussian to relate this derivative of the free entropy to the posterior average, which is the optimal estimator under the mean square error loss. Moreover, the optimal performance of our algorithm can be related again to a derivative of this time the averaged free entropy, thanks to a standard result in Bayes optimal analysis, which is the IMMST theorem, which gives the mean square error of models with additive Gaussian noise as a derivative of the average free entropy. So the moral of our proofs is that one needs only to compute the free entropy, and we spend a bit of time computing the asymptotic value of the free entropy. So let's look at this normalization factor or its log, so the free entropy. So the normalization factor Z of Y is the integral over our variable of the posterior distribution of the numerator of the posterior. So the prior here in green and the noise channel here in blue. So the noise channel is Gaussian, so we have a quadratic form to exponential, while the signal is generic, it's just rotationally invariant. So to compute this partition function, we can leverage rotational invariance and do a singular value decomposition of our integration variable S. So we write S as U times L times V. U and V are rotation matrices, singular vectors matrices, and L is a diagonal matrix of singular values. And the first thing we do is we gather all terms depending only on spectral quantities, so only on singular values L, in this black box function F. We have an explicit formula, but here just think about F as the collection of all terms depending only on singular values. And here you will find terms coming from the prior, which is rotational invariant, and then depends only on L. From the change of variables, because we have a Jacobian going from S to U times L times V. And some exponential terms coming from the Gaussian part. And these will be easy terms. They are spectral terms which we can deal with nicely. The difficult part is here shaded in orange, is the singular vectors part. It's an integral over singular vector matrices U and V with uniform measure because of rotational invariance, mu of U and mu of V, of the cross term coming from the exponential. So we have an U times L times V, so this is S times Y transpose. And this integral is called in the literature a rectangular Harish-Chandra-Itkinson-Zuberi integral, HCIZ for short. And this is really the difficult term in our computation. So to compute the free entropy and to obtain then our optimal estimator and performance, the thing we need to do is compute the asymptotics of the HCIZ integral, and then everything is easy. Here I'm hiding a small technical step that allows to deal explicitly with the integration over the spectral matrix L, which requires some concentration argument and using Nishimori identities, but I will not tell you the details. You can ask me if you're curious, or you can check the details on our paper. So our more technical result that we give in the paper is an explicit formula for this complicated HCIZ integral that is needed to compute the free entropy. So we provide an explicit formula, and this is very rare. Let me remark that. In a specific case of the HCIZ, so not in general, but when the matrices, it depends on Y and L. So if you don't remember, the definition of the integral is here shaded in orange. It depends on L and Y, and it's integrated over U and V. So the explicit formula we have is for the case in which Y minus L is a Gaussian matrix. And this is the case that we find in our computation. In this case, this integral is again an extensive quantity. It's exponentially large in the dimension of the matrix. So to perform the limit, we take the normalized log. And this will converge in the dimensional limit to this expression. Again, it's not very complicated, but not very nice to look at too. It depends on the aspect ratio of the matrix R1 and on the spectral densities, on the singular value distributions of the matrix L and Y. So it's very similar in nature to the formulas for the denoiser and the performance that I've shown you before. And the reason is that those two formulas come really from this asymptotic characterization. And getting this explicit formula allows us to find an explicit formula for the free entropy from which we can derive the optimal denoiser and the optimal performance, as I argued before. So here, let me stress a link to matrix factorization to go back a little bit to my motivation. So matrix factorization and denoising are really similar problems. And one of the similarities is that the free entropy, so the log of the normalization of the posterior of matrix factorization and of denoising with factorized prior are actually the same. So by computing this free entropy, we actually accessed some asymptotic quantity also for the matrix factorization problem. It's still an open question to me whether this knowledge helps and in what sense to get some insight in this more difficult problem. So before I conclude, let me give you a glimpse of what's around us in the literature. So there is a big line of work regarding spectral denoisers, so rotational invariant denoisers, related to the problem of cleaning correlation matrices, for example, for applications in finance or biology, where you have a correlation matrix and you want to be sure, you know that it's noisy. You maybe know also where the noise comes from, and you want to clean it before using it in some estimation or some other field-specific task. So in this line of work, they tend to study rotational invariant estimators in more generic prior conditions, so not for rotational invariant priors, and not only for Gaussian noise. This is like a more general framework than us, but this generality comes at a price that in general they have no prediction for the mean square error. So they cannot predict how good their estimation procedures will perform as a function of the signal-to-noise ratio. A smaller line of work already studied Bayes' optimal analysis of the denoising problem, and notably there is this work by my co-workers, so Antoine, Florent Jacala, Lenkas Deborova, and Marmezard, in which they studied the symmetric case, so the case in which all the matrices we have spoken about are Hermitian. We generalized their analysis to non-symmetric case, and let me stress that this is really non-trivial because random matrix theory tends to behave in a much uglier way when dealing with non-Hermitian matrices. And finally, there is a big line of work about the asymptotic of the Harish-Chandra-Iskinson-Zubair integral. It's very mathematical in a sense, so they give very general characterizations of the asymptotics of these integrals, but in some sense they are a bit impractical. It's difficult to use them in explicit computations, mainly because they are given implicitly, for example, as solutions to PD partial differential equations. So in our work, we again generalize some explicit solutions that were available in the symmetric case to the non-symmetric case, which again is a non-trivial task. Okay, so I think that I told you everything I wanted to tell you. So let me wrap up with my talk. So in this work, we characterize the estimator and its performance of the problem of denoising rotational invariant rectangular matrices in Bayes optimal conditions. So with the full knowledge of the generative process of the matrix Y. And as a technical byproduct, we provided a new explicit formula for the HCAZ integral under some specific conditions. Some questions that are still open, at least in my mind, and that I will try to focus on in the future are, what are implications of these results for matrix factorization? Because as I've told you, for extensive rank matrix factorization, let me stress the extensive rank. Now we have the free entropy of the problem, so this may help us, but it is still not clear how in my mind. Another question is how to step away from this highly symmetric rotational invariant setting without removing the correlation that it brings. We would like to find a more general class than rotational invariant matrices to see if our analysis can be carried over. And finally, can we analyze the mismatch setting? So the setting in which a statistician has partial knowledge or flowed knowledge about the generative process of the observation. So with that, I would like to thank you. And here you can find the coordinates of our paper and our code. So thank you very much.
Thank you, Vittorio. So we now have time for